Hello everyone, and welcome to today's session on crash testing. We all spend time in vehicles on a daily basis, so this should be very relevant for us all. And until the day comes that autonomous vehicles control the roads, drivers will take unnecessary risks, make bad decisions, drive in a distracted way. Hopefully that's not you. My name is Justin Bashinsky, and I'm a regional manager for Trilion Quality Systems. I'm located in the heart of Motor City, Detroit. And we are an optical metrology lab armed with powerful tools for measurement. I wanted to expose you to some of the things that we do here to make your life safer, from coupon testing to crash testing. And perhaps it will start up your creative horsepower as to our potential. So come along with me for a crash course in testing. Okay guys, so different crash testing groups have different goals. Some want to test the safety standards, others want to learn more about accidents, reconstructing real-life accidents. Mostly, I deal with car makers that want to engineer safety systems that will keep their customers safe and help them sell more cars. And this includes testing of novel materials, new safety designs, and often validating simulation models, which means testing how product designs perform in dynamic situations. Crash labs need to understand acceleration in any particular direction, understand force, velocity, relative displacements, and resulting deformations. And they'll use any number of different sensors to complete this testing. And often on the perimeter of the test, you'll find high-speed cameras for witness photography. This photography is used in combination with the sensors to help investigate what is actually occurring. For instance, on the right of the screen, the dummy's head will have a three-way accelerometer inside that tells the engineer an acceleration reading. With the vehicle now at impact, he or she will look at the video from the witness photography as a roadmap to determine what was occurring at the time of the accelerometer reading. So there's a bit of juggling that takes place between the data sets. So at Trilion Optical Labs in Detroit, we perform non-contact measurements. For crash testing, we often are using our Aramis solution that you see here. It is two cameras arranged as a single 3D sensor. Its integrated software, Zeiss GOM Correlate, puts the images from Aramis together and makes the measurement. So the user sees both what is occurring and the quantitative results represented together in the video, so there's no more juggling of data. Aramis is capable of making measurement of the following from the images it takes: 3D shape, rotations, displacements, strains in full field, both principal and directional. It tracks velocities and accelerations, and it can look in the frequency domain for modal analysis. With regard to impact, other conventional sensors often lose their value during collision, but the Aramis Optical Strain can measure straight through because it's non-contact. We find that this is very helpful in more fully characterizing the event. So you might ask, how does this work? Aramis uses a principle of triangulation between its two cameras to identify and track points along the surface. We'll place dots on the surface of a testing object. Each one is automatically identified in the software as a 3D coordinate. For point tracking in the time domain, this yields 3D velocities, 3D accelerations. It doesn't have to be a stick or dot. We use Sharpie markers, paint pens, sometimes vinyl stencil. If we're interested in a more holistic measurement of strain or displacement fields, we will apply a speckled spray paint pattern on the surface to create thousands of tracking dots. There is no upper limit to our point tracking. The main idea here is to find a correspondence between control points in a reference image and images of a deformed state. Because we measure so many things at once, we apply to many different testing groups. Let's focus in on some standard tests that we perform here for crash and safety groups. But there are a number of standard tests we perform that I can't get to in the scope of this webinar. Whether you are a CAE working with material models for numerical simulations, or you're a test engineer characterizing the mechanical properties of materials, you know that working with accurate material parameters is crucial for making the right decisions during the design phase of your product to ensure the best performance over the entire life cycle. Let's start with tensile testing, where Aramis is replacing extensometers and strain gauges with a more accurate, more full data set with far less time spent setting up. Since the Aramis sensor is high resolution and it measures in full field, we can see local effects like these. Luder's bands, slip bands. They're localized bands of plastic deformation found in metals. We see these a lot in low carbon steels, and our customers tell us that band formation can pose problems in metal forming. One of the major use cases for Aramis is the replacement of extensometers in material testing. Aramis has similar accuracy but lower user variability, and the full field data results contain much more information as it provides global as well as local plastic strains where the necking occurs. Because of this, the material properties calculated are much more accurate in the high strain region, a region of particular interest for our crash safety customers. The stress strain curves and material data are automatically calculated with our software according to common ASTM and ISO standards. The Aramis software, known as Correlate, is an engineering toolbox for arranging the data. We perform high-speed material testing from 2 meters per second to 20 meters per second. The design engineer needs to know the material's dynamic properties, as material behavior may differ substantially with dynamic load. This is a tensile coupon at 45,000 frames per second. The whole event occurs under 2 milliseconds. You can see we constructed a section length down the center of the coupon. This is a virtual sensor that will illustrate the elongation and ultimately the failure. High-speed tensile tests provide characterization that considers the dynamic strength of a material and help to maximize its use in product design. In our experience, the CAE team often wants to see the high strain area just at failure so that they can best update their strain rate distribution for the FEM, and they can maximize the lightweight potential of their product. So if we go further into dynamic material characterization, this will often include compression, looking at the strength of material, determination of the compression modulus, determination of the yield loci. We can perform these types of tests at high rate. This one's at 45,000 frames per second, and at high temperature. It should be noted that since we're non-contact, we are agnostic of temperature. Of course, the extreme temperatures pose some challenges to us, but we have lots of capability here. Here's a simple strain evaluation on the surface of a cylinder. This is under compressive load, and these tests often lead to more economic materials being used. Often this is for enhancement with composite fiber reinforced materials. Getting even faster now, the split Hopkinson bar is used for ultra-high performance testing. It can be used to achieve really high strain rates in excess of 1 million per second. Put simply, this is an instrumented loading device for dynamic material properties, where an elastic wave pulse will run through a material sample. Commonly, strain gauges are installed on the bar to determine what the transmitted pulse on the material is. But with Aramis, we can replace those strain gauges. At 180,000 frames per second, the sensor is positioned to image the sample material. It's been patterned, and the strain measurement of the sample is taken directly from the surface deformation. Let's now turn to something a bit closer to home for me and focus in on some automotive applications. Crash box testing is a vehicle collision test, and it's really all about reducing repair costs in low-speed collisions. Researchers will be interested in looking at energy absorption and the stability of the component. Here, we're going to consider the simulation versus the experiment, the FEM versus Aramis. We can take the finite element model, the FEM, and take its shell or its surface and compare it directly in our software. The model will have a prediction on the force-displacement relationship, as you see here. Here is the Aramis measurement, and the beauty of the Aramis data really is that it has so many points to compare to the model. The CAE team just loves this. They typically do ask for mesus strain. That's primarily because they're concerned with yield or fracture. You can see the profile of strain in that top graph and the discrete points graphed across time in the bottom. Another likely component test measurement that we perform is a crush test. The surface measurement here is longitudinal strain. You can see the material collapsing. In the center graph, you can see the velocity slowing as the material folds on itself, providing resistance. You can also line this with the load data as we typically record it and trigger from it. Okay guys, airbags save lives for sure, but in recent years there have been some airbag related injuries and even some fatalities. That said, airbags are essential and they're in more places than ever before. It's important to understand their occupant interactions and how they often bounce off other car components like the windshield before they fully deploy open. Luckily, Aramis can help. It can capture the full deployment of the airbag as seen here. A pre-patterned bag was packed and deployed for measurement. All this considered, there's new regulatory requirements. So there's new simulations of folding and deploying airbags. These are all really useful, and Aramis can validate these assumptions. Here's a video showcasing the gas flow, momentum, and overall energy of an airbag deployment. You can see right above that's a high-speed Aramis looking down to image the event as it absolutely explodes. Pretty cool. So here's the resulting data of that housing we saw in the past video during that initial opening sequence. And from this, the user was able to characterize how the bag emerges from the housing. Aramis can also track deployment of airbags to better understand their full shape and contour. This is done a little bit differently. We're not patterning the airbag. Instead, we're using a contrasting background so that we can track the lines of the full shape and contour of the bag. In this case, the software automatically can track the contour of an elliptical object. This is a quick way to measure the farthest distance the bag travels and its velocity throughout the deployment, key features of the regulations. Next, we have windshield testing. The windshield can be multi-layered with noise absorption, infrared reflection, wire heating, and sometimes researchers need to understand the cracking for safety reasons. Other times, it could be that they want to verify the vulnerability of someone exiting the vehicle during an accident. Numerical simulation continues to get better, but this multi-layered material is quite hard to understand. Aramis can help to verify the deformations. In this case, to characterize glass is very difficult. It's very brittle and hard to capture. We use third-party high-speed cameras to configure an Aramis 3D setup. I just want to take a moment to consider the Phantom TMX. It's Phantom's best camera out right now for performing this type of measurement on glass, where you can really get high resolution on these deformations. But don't take my word for it. Check out the Slow-Mo Guy's video on YouTube. It's labeled Smart Plug versus Car Windshield. Pretty cool, right? So let's get back into it. We're definitely going to use high-speed cameras for our Aramis configuration. But during the setup of the test, the full fixture needs to be patterned so that we can apply a rigid body motion correction to remove the global motion that occurs during the test. So the head impact takes less than a second to fail, and in that time, Aramis is able to image, measure, and show that ultimate failure of the windshield. If you look at the template, we're pointing out cracks as they propagate across the glass. We've exaggerated the displacements to make it a bit more obvious as to what's occurring. Good project. On now to a side impact test. The side impact at 35 miles per hour is a standard crash test performed by safety groups. This test is all about structural integrity and about minimizing the intrusion into the vehicle. Aramis will be positioned opposite this sled to see inside and evaluate the deformations experienced. Here is the vehicle before collision. Our Aramis sits on just the other side and a safe distance away. Here's a quick video of the Aramis images. Notice the target dots in the field of view. These target dots now become 3D coordinates for tracking, and we've created components for the B-pillars and the interior door. We use the left side B-pillar as a reference as a rigid body so that we can isolate the deformation and correct for that full global motion experienced by the whole chassis. This allows us to inspect the points for Z direction travel and best understand the total intrusion into the vehicle. Now we can turn our attention to sled testing. We see witness photography being used regularly in sled testing. Why not use Aramis to quantify those same images? Seat and belt systems are common things to test in simulated sled tests, so we place target dots anywhere we want data. Again, these are just stickers that become 3D coordinates for tracking, and here we have the sled, the dummy, and the seat dotted up for tracking. Here's a video of the test. Most labs end up with a video just like this from their high-speed witness photography. They'll look at the measurement bar in the background you see along the wall to best determine how far things moved during the sled test. Instead, here's Aramis giving us an evaluation of the full motion with vectors telling a story of magnitude and direction. Here the sled is our frame of reference, otherwise known as the rigid body motion correction for the measurement, so that we can isolate all motions relative to the base of that sled. The dummy head is always of importance to researchers. They'll want to understand its movements in all directions. For further analysis, Aramis users can construct a local coordinate system and track pitch, yaw, and roll of the head. Once points are inspected, the data will plot itself in the diagram, and the software will export all points in CSV file format. Aramis can also track and plot motion trajectory during a crash test. It gives researchers an understanding of the full 3D motion. When conducting sled testing, it's important to use different sized dummies and different seat positions. These are often referred to as H points, a position between the hips for the dummy. Aramis uses a touch probe that is automatically identified and tracked when brought in front of Aramis for dummy positioning. The touch probe works much like a CMM. You use it to get points that are obstructed from view and even measure lines or curves of a seat. So for sled testing, there's a number of regulations that Aramis can help to meet for dummy positioning before the test. Here's another amazing Aramis view of a Chinook helicopter crash landing at NASA Langley Research Center. Here you can see the color map measurement of displacement in the Z direction. Really large dots here, guys. And at that same facility, here's a strain measurement on a small plane. An important part of product qualification testing in aerospace, Aramis Optical Strain is used to understand the effects of an airborne bird strike and the resulting damage. Frozen birds up to 8 pounds are launched at 400 miles per hour. The result is this impact. For this next sequence, we reached out to Phantom High-Speed Cameras, Kyle Gilroy. Kyle's helped us in the past with his expertise. Also, he's part of this really interesting gun project you see on the right that he completed with Trilion. Kyle helped us to create an Aramis configuration using the Phantom T1340s, a set of 4 megapixel cameras that are very capable. You can see them set up in our office on the right side there. We use these phantom cameras to explore a drone crash example. We know NIAR works with FEM on drones, and we thought we'd pay tribute to them. Take a look at our speckle pattern and target dots for tracking. We have the body and the propellers ready to go. Getting a drone to crash is easier said than done. In the end, we had to throw it against the wall. Here's a look at the tracking of the propellers. If you look closely at the tip of the prop, you can see it has the most z-direction displacement. For this data series, we tack the coordinate system to the body of the drone so that our measurements will be relative to itself. You can see that on the right side there. Quickly pulling out the X direction movement, we begin to characterize what happened to the drone top during the event. You can see one of the top left propeller arms hit first against the wall and cause movement throughout the top. And here is the Z direction for the drone crash. You can see the movement oscillating between the propeller arms. Pretty violent crash. Anywhere along the speckle pattern on the body of the drone can be selected as a discrete location to pull data out. We went into the image series and selected a point right on the top of the drone, and it graphed out this nice looking DZ data. It reveals to us that that top of the drone traveled a full 1 millimeter in motion, not a whole lot, and the drone itself seems to be in good working order, as if I hadn't even really thrown it against the wall. So kudos to the designers of this product. All that data is great, but you don't have to export it out and crunch it in MATLAB or some other program. It can all be done right within the software. The comparison of the FEM shape, displacements, strains can all be done under one roof. Our software works great to import the FEM and conduct comparisons. We even allow for native file types from the following list of software choices. Sometimes they even provide our file type as we work together. If you're looking to speed up your simulation verification process, our software is designed to save time. This is where Trilion is very powerful. Aramis bridges the gap between testing and simulation. Aramis users synchronize their measurement with the steps of their model. There's a common coordinate system that's established between the two, and often it's just an alignment to CAD that completes this. There's no inherent length scale to Aramis. Users can choose the corresponding subset size that matches best to their FEM nodal data. There may be different models behind the derived results, like strain, so our users have tutorials to help them bring these computations together for comparison between the two. In this example project, the FEA import is completed and then aligned with the measurement. Now, a custom user-defined equation is created. This will be a displacement comparison between the two. So the Aramis measurement is selected, the FEA is selected, and expression is written. The expression of FEA minus the measurement will reveal a color map of disparity across the entire surface of the test object. The FEA can be updated accordingly. This is a very quick way to check your FEM assumptions or possibly update your boundary conditions. Customers contact me when the simulation is not possible, but often, even when they have a model, the Aramis data will reveal areas of influence, sometimes critical, that make a difference in the test. And understanding these details helps to make critical design choices. Remember, this Aramis data is based on real measurement across hundreds or thousands of points of data, not a series of assumptions based on material cards. If any of this piqued your interest, go download the free evaluation software, Zeiss GOM Correlate. Try it out. Try out some of the sample files. If you have a high-speed camera, contact me straight away so you can get started today making quantifiable measurement from images you probably already take. Thank you for your time and consideration. I'd be happy to answer any questions you might have. Okay, guys, let's go ahead and get into the Q&A portion of our presentation. Thanks for your attention, and hopefully you liked some of the cool applications we went over. We actually do a fair bit of support here in Detroit for the crash and safety labs. And so we really wanted to just give a nice slice of the different types of tests we do. There's a lot we can't show, a lot of really cool stuff we do. I'd be happy to talk offline about that with anyone, but to be able to show it in a public way would just not be possible. I did get some questions as we went through the presentation there. It looks like I'll just go ahead and try to answer those in a chronological order. The first question was, that speckle pattern looks difficult. How hard is that? We actually have a lot of people say that to us. It's not hard at all, actually. I think that maybe it does seem to intimidate people. But just like anything, there's a bell curve to it where most people will be fine. At the extremes, you might find people are very advanced and still others just won't quite get it. But a lot of people say it's like an art form. I don't think it's an art form at all. We actually have a process that we train our customers to perform, just basically calculating your dot size, speckling on a blank surface to get close to that dot size, taking a photo with Aramis, zooming in and counting the number of pixels, have your part ready. So when you match the appropriate pressure for the dot size, you turn to your part. And it's a pretty straightforward process. But you know what? If it still proves to be difficult, if you don't want to follow that process, we have sponges, bristles, stencils, stamps. Let's see. We have laser etchers. We even have an inkjet printer that will print consistently a pattern, so you don't have to deal with the nozzle of a spray paint can if that's the issue. Hopefully that answered it well. The next question is, what is your accuracy for Aramis? It's pretty straightforward. It's just a function of the field of view and the spatial resolution of the cameras. So, Aramis is 1/100th of a pixel in plane and 1/30th of a pixel out of plane. So if we were to take a 12 megapixel system, we have higher. And of course, when you're shooting it, for crash at some of these high speeds, you will experience lower resolution setups. But with a 12 megapixel system at a 1 meter field of view, you'll be 2 to 7 microns noise floor. If you want better, you can lower the field of view if your interest area is small enough, or you could increase the spatial resolution of the cameras, which is totally possible. And so these are, that's the function. It's just as simple as that, I suppose. So hopefully that gets it across. And if you have a specific use case, be happy to look at the accuracy that you would need versus what we could perform for you. The next question is, what coordinate system does your sensor use? I guess, it probably arised from the drone test. Automatically the software will create a coordinate system. It's normal to the page. We often, especially when we're working with automotive OEMs, we use their CAD. We could use the FEM, bring it in as a CAD. We import and align it to the CAD to get it into car coordinates. This is typically what we're up to because we want all our measurements to be in car coordinates to get us in that correct coordinate space. If that doesn't exist, then the coordinate system is actually totally flexible, really easy to work with, even allows for the user to have local coordinate systems apart from the global. So that part is pretty straightforward. If you have further questions, I'd be happy to dig deeper into that. Next question is, how fast can you record at? It's not so much about how fast we can record at, because I guess in a way, the sky is the limit. We can pair any two digital cameras together to make a measurement. So 1 million frames per second, sure. It's more about your specific application. the speed, lighting, area of interest, the duration of the event that we'd want to consider. And, really, there are more options than ever before. And honestly, it just keeps jumping ahead as technology gets better. So, I would say that how fast you can record at isn't really necessarily a concern. It's going to be a combination of different challenges. If you do, in fact, have something that's really fast, there might be some other challenges that make things worse. But I'm happy to explore any use case that you have in mind. Always ready to get on the phone and talk that out and explain it to you so you can see what we'd be capable of. And it looks like we have another question that came through here just a moment ago. What is your range of specimen structure sizes? I guess for this, I would say 5 millimeters to 5 meters off the shelf, ready to go. It's probably the quickest way to look at it. 5 millimeters all the way up to 5 meters. If you want something outside that, we can make it happen. But there may be some trade-offs if we go really small or if we go really, really large. So that's hopefully a pretty straightforward answer for you. What is we have another question just come through. What is the calibration process? Minimum 13 pictures of a calibration artifact. If you're taking longer than 5 to 10 minutes, then you're doing it wrong. There might be people scratching their head at me over that. The way that we train our customers here, especially we use a lot of fixed-based systems. Our customers are done in 5 to 10 minutes for our calibration. It really shouldn't take any longer. I would say if you're setting up a sensor from a disassembled starting point, then it's going to take longer. It's going to require more setup. But our sensors now come with VDI certification. So we've got optical metrology level traceability to our sensors. It verifies your ability to make accurate measurements. All our artifacts are NIST traceable. I would say calibration should be done according to the sensor that you have and your work environment that you have. So if you're in like a quiet lab, where you have careful colleagues, of course, we do come across customers like this, maybe not so often in automotive. Oftentimes they'll have a sensor that they can get away with calibrating once a month. And that makes sense for them. But if you're someone that's in the stamping press, or if you're next door to the stamping press, which some of our customers are, then you feel the ground shake beneath you throughout the day. And, you're going to need to calibrate before each important measurement you need to calibrate. So actually, I have another question come through. And the question is, can I measure stress? Not directly. We measure displacements and strains. And so our software will calculate stress for you as long as you provide the dimensional area for it to consider that. So that's pretty straightforward question and answer. I think that, we have another one coming in. Oh, okay. Thanks, Doreen. Doreen is thanking us. Awesome camera for sure. Thanks for the well wishes. Appreciate that. Thank you. Yeah, thanks for the amazing product. With the TMX camera, Phantom has really made a jump forward in technology. We've noticed that. Actually, my colleague Charles is on site at NIR, and he's got some hands-on experience with the TMX. He's done some DIC work with it. So he's put together an Aramis configuration, and you should ask him about that so he could show you some really cool footage. I did not include it here, although I maybe could have. But maybe it's something, if it piques your interest, you'll go find that, or perhaps Charles can point that out to you. So, okay, great. Are there any other questions or that I can help with at all? There are certain applications or areas in industry that make a lot of sense for what Trilion does. And this is really one of them, guys. The safety crash lab, it's absolutely benefits from having an optical sensor that can take measurement of this style, of this sort. It saves them a ton of time. It gives them so much more data. It allows them to characterize things that they couldn't before. What we find is when we're on site in the crash lab, we're well loved, and our data goes a long ways. We're often lowering the number of iterations for these very expensive tests. So, did we get another question come through? It doesn't look like it. No, I don't think my video has been on. I apologize about that. At least I get to say goodbye to you guys. I think that's it for our time today. So I appreciate everyone, and hope you have a great rest of your day, and hope the NIR event goes well. Thanks, guys.